All right. Good morning, good afternoon, good evening. Welcome everyone to GE Digital's webinar. We will be discussing business value and technical challenges within industrial data science. My name is Cody Bunce. I'll be moderating. It's going to be a quick 30-minute session today, along with two of our esteemed data scientists who I will introduce in just a minute here. The three of us will provide some content for the first 20 minutes or so, and then we'll have 5 to 10 minutes for Q&A at the end. Please keep in mind, folks, that we're in audio listen-only mode, and if you have questions, which we would love, please just submit them via your Q&A box that should be at the bottom. And if you want to submit those while we're talking, feel free. Don't feel like you have to wait till the end. Great. Okay, so given we have limited time, let's jump right in. So to help frame our conversation a little bit, when we look at manufacturing as a whole, some macroeconomic trends that we are seeing our customers experience, as well as what we are experiencing as GE as a manufacturer, right? We've got over 400 manufacturing plants globally. These trends are creating some interesting opportunities for the manufacturing market in general. The first thing we see, falling costs in automation hardware, specifically things like sensors and robots, in addition to the existing falling costs that we're already seeing in IT and computing power. Number two is the rise in the power and promise of machine learning, with really maturity being realized slowly but surely in synchronized robotics and self-driving cars. And then finally, new demand, right? So what we're hearing from customers, as well as customers of our customers, is that manufacturers are asking for outcomes, right? Specifically the outcome that the product that's being manufacturing enabled versus just providing a product. And this is relatively new. The combination of these trends is definitely creating some opportunities, and it's being validated in the market by IDC, which is an industrial analyst firm. And they've reported that by the end of 2018, 40% of discrete manufacturers will introduce an as-a-service business model. Not that they'll have it refined, but they're going to be dipping their toe in the water, so to speak. So for companies who want to take advantage of this and go down this path, it means that every aspect of your business will be impacted, including the product itself. And to even be equipped to start this journey and start leveraging some of the trends that we've just discussed, having mastery of and making sense of your industrial data, that's going to be critical. And that's really what we see as step one. But it's a very critical step one. So this is where we see data science playing a role, and it's where data scientists played a role internally at GE Digital. And with this in mind, we have two esteemed colleagues, data science professionals, Ajay Anand and Sergey Patsko. They're going to be discussing differences in data science methods that can be applied to well-structured data, low-quality data, as well as how you can identify where in your business data science can make an impact and potentially put you on a path to generate some of those new business models that we were talking about earlier. So Sergey and Ajay, please take it away.
Thank you, Cody, for the kind introduction. Talking about as-a-service business model, I agree that for many manufacturing companies that will be crucial to staying competitive, switching to such as-a-service offerings. And if you think about GE, then we actually have done it already in many other industries, aviation as an example. We are not selling jet engines, for example, anymore. We sell time on wing, and airlines pay per flight hours to us. So in such an outcome-based business model, the only way for manufacturers to earn profit is to be more efficient throughout the whole manufacturing process and product support operations, because most often manufacturers now are absorbing the maintenance costs. So having said that, based on the experience that our GE Digital Data Science Services team earned serving industrial companies, we see multiple areas where manufacturers can benefit from data science. You can see such areas on your screen right now, but we would probably pay attention to just a couple of them right now in this 30 minutes. One is throughput improvement. How can a manufacturer produce more products without actually making investments into acquiring new equipment? And to do that, one of the key and powerful analytics will be estimation of machine life. So you can use historical maintenance records combined with sensor data to build mathematical model and find attributes that contribute most to machine failure. They can be vibration sensor data or temperature data, production quantity data, different types of attributes. Then we usually apply natural language processing to find out insights in maintenance records. And through those insights, we inform ourselves on most important attributes, as mentioned by engineers, and then we apply data science to the data generated by those sensors that we have found from the maintenance records. And using that analysis, we can find the thresholds that attributes cross prior to machine failure. It can be more complex, then it's not just alerting, but data science techniques can help find the right combination of factors to track. And through tracking those critical levels, you can create machine degradation score, which finally gives you the ability to control the machine life and do such things as predictive maintenance. So this is one of the key applications of data science in manufacturing, machine life and predictive maintenance. And Ajay, could you talk about the second one, which we've marked as an important, which is a scrap reduction?
Sure. So along with the throughput improvement, those same factors that we find there can also improve scrap. So our goal here would be for scrap reduction. So as we said, we use the data to find factors on the factory floor that contribute the most to scrap, and those factors can be coming from anywhere. There's a whole bunch of different data systems that are available to us. And the first goal is to find those right factors that, when turned on, produce defective products. So why is data science important here? Well, before, this used to take a lot of really, really expensive controlled experimentation. But now, using the data that is collected from production runs, less experimentation is really needed to dig in.
Perfect. And talking about, so we have already started to talk about important applications of data science. Now let's switch to the next slide, which we see on the screen right now. And could you, Ajay, just let us know what is the difference and what are the challenges that you specifically see as a data scientist while working with manufacturing companies?
Yeah, sure. So on this table, you can see a lot of the major differences, but specifically, I'd mention cost and value, frequency of data, and physics-based models as being the major differences between data science in the manufacturing industry and elsewhere. So in commercial or internet data science, there's more frequent and drastic experimentation available, like mentioned before. For example, one aim of internet data science is to improve click-through rates, or the rate at which customers click on something, normally like an advertisement or another link. So thousands of people see these advertisements in a given minute or hour, and that is what you're essentially trying to optimize or improve upon. So this gives data scientists a lot more data, and even more so, a lot more events to work with. So the experiments they run here are pretty cheap and don't have any large impacts on their process while they're actually running those experiments. The difference is in industrial data science, you require very close control on experimentation. And we usually have less failure events data in comparison to the commercial use cases. So the frequency of an event in the manufacturing setting can be really rare. And when a machine breaks down in process, all processes after that machine are directly impacted. So this could mean that a diverted production line is needed, or it could mean that the production has to stop completely even. And this is a huge potential cost associated with this type of a failure. The other challenge here is that oftentimes machines break down, once a year. So most of the time there isn't enough data points to do traditional machine learning in the same way as internet machine learning is done. So we have to supplement the machine learning models with physical models as well.
Okay, so basically you are saying that if you would have a lot of historical data points, then we can train our machine learning algorithms to predict something in the future, but in manufacturing, sometimes you don't have a lot of failures, but the cost of failure is high if it happens. So that is why machine learning is not enough. So can you maybe give us an example to better understand this?
Yeah, absolutely. So on your screen, you'll see a project that we just ran through. It was with additive manufacturing, which is 3D printing for metal, and they had a rare defect problem that they wanted to understand and detect. The only way that quality issues can be detected today in this process is through CT scanning the metal parts after they've been 3D printed and go through additional processing, which is inefficient, very expensive for the thousands of parts that they plan on printing, and also doesn't really give you a clear picture of when that defect actually occurred. So the customer provided us with a signal that measured the intensity of emitted light from the impact of the additive laser and the powder metal material, known as a melt pool. Using that signal, we wanted to see if we could classify the rare defect that they were experiencing. But unfortunately, that raw signal wasn't enough information to inform a traditional predictive model. So we worked with the SME, or subject matter expert, to come up with some physical features derived from that signal. We developed features from the signal ranging from very simple features like scan speed, which is just using the X and Y geometry to determine a speed that the laser was traveling at, all the way to some very complex features like thermal mass estimator, which used a recursive algorithm on the X and Y 3D geometry plane, coupled with the formula for heat loss and conductivity. And these features were enough to inform a model to accurately predict the rare occurrence defect, and also, in addition, reduce the amount of data processed and calculations needed, which was absolutely critical for the near real-time app that they were asking us to develop for them, which gave them early detection on these defects. So without the SME, the subject matter expert, to help us derive these features with physical meaning, we would never have been able to create an accurate model just based on the signal itself, the raw signal itself. So I guess the point of this really is that oftentimes the model is not necessarily the answer, but instead the actual features derived and physical features derived from the data give you a much better picture of a solution.
Okay. So basically you already started to talk about some kind of solutions that you can offer using industrial data science, specifically physical features and using physical features. But before we go into other challenges you see and solutions you can suggest, could you go maybe through the process so that for our audience to understand what is the overall data science process that you apply when you're solving manufacturing problems?
Sure. So the slide on the screen right here depicts what our framework really is. And we follow this framework that was developed after being successful on a few different manufacturing projects that helped us kind of hone in on this process. So the first step here that we're going to take is to establish what the project will be about. So what is this hypothesis that we want to answer with this project? And a hypothesis in this framework is not only connected to the research or academic nature of what a hypothesis is, but also to the business objective itself. For example, what factors contribute the most to our plant delivering late parts? So that is a hypothesis that could be rooted in either research or in business objectives, and we kind of merge those two worlds with the rest of our project cycle. So the next step would be that we figure out how we're going to rank whether or not we are successful by establishing criteria for success right up front. So that's a very important step because when we get to the model development, we want to know what we're really trying to optimize, and this gives us that picture of what we're really trying to hone in on and trying to improve or optimize or reduce. So the next step then would be that we establish the data sources that are going to be available and also relevant to painting a full picture of a solution for the original stated hypothesis. This is also a very, very important and sometimes very difficult step that we'll talk about a little bit more later. But we set up a pipeline with our data engineers to collect, merge, scrub, clean all of the data that we're able to collect and start our exploration process. So in this step, we also develop and validate features that are of interest, like some of the features that we mentioned before, rooted in a physical nature and has some type of meaning behind them. So after this step, we're finally ready to develop a model solution for the hypothesis using these validated features. So once we validate the model itself using the scores that we established as criteria for success, we're then able to deploy that model against live production processes to show how the model performs in a live system. So although we're developing these prototypes, it's not enough for our customers to just have a prototype. They want to prove out that solution on a live system to really be able to see its effectiveness.
Yeah, thank you, Eji. Well, I would probably add here a little bit from the business side that the first step, defining the project hypothesis, It sounds like obvious, but we have done over 150 data science engagements over the last 4 years, and in the beginning of our practice, very often our engagements would become kind of a scientific exercises a little bit when our internal or external customers, they will tell us, hey, here is a lot of data, could you find some insights and help us improve some metrics? So we found out that if you start from data, you can be misled very, very soon. So that's why it's critical first to think about the business outcome, what will be the business value of solving this problem, and only then talk about the data that is available around this problem and then follow this process. So thank you so much for describing this process to us, Ajay. So what are the most challenging and critical steps from your perspective, from the data science perspective of manufacturing in this process?
Sure. So I would start by saying that every single one of these steps definitely has its own challenges that are pretty unique. But in my experience, the biggest challenge step that I've faced has been at the explore the data and develop the features step. So just to start with, so everyone understands what I'm talking about, a feature is a variable in your system that you're using to predict a response. And that response variable is typically what we want to predict or optimize on. So before a feature can actually be used, it needs to be properly analyzed and studied to ensure that it's variable enough to explain some of the changes that we might see contributing to our response variable. So I'm going to highlight one of the solutions that we made here for one of the problems that we had with the data that we were getting. So one of the specific challenges that we have run into is with time series signals. Time series signals are not new, by any means. They've been around forever. But commercial data science projects or internet data science projects don't use time series signals very often. Manufacturing data science projects, on the other hand, use time series signals almost always. So when we say time series signals, we're talking about sensors, anything that has to do with reading a signal from a sensor. Manufacturing. So I mean, what our team actually developed was a reusable package called TSTK, which is a time series toolkit to help us really quickly understand and ingest a time series signal. So that's what's being showed here on the slide is an example of the output that TSTK allows us to get to almost immediately. It allows us to really easily visualize the signal and understand where there are gaps or missing data within that signal and quickly identify patterns within the time series to help us kind of move in the right direction quicker. So TSTK also helps us generate features from the time series, which includes imputing many different possible values for missing data. So if you have missing data in a signal, essentially what you want to do is you want to fill that data with something. So it could be anything from the average to the min to the max to the standard deviation. TSTK helps us do that very quickly. So although I keep bringing up this reusable asset, it definitely doesn't solve the actual challenge, but it gets us moving in the right direction quicker than before. And we've developed a few of these reusable asset packages so that we can attack the common problems in manufacturing that we run into quicker. Another example is I won't get into it, but it's called TNTK, which is a text mining toolkit. So that's something that helps us with our maintenance log data.
This is perfect. And any other challenges you can see
definitely.
in this process?
Yep, definitely. So I have another slide up here that depicts another challenge that we have with the data that we work with in manufacturing, which is in traceability. So manufacturing is a complicated process which often has lots of timestamps with product in different buckets at different stages in the manufacturing process. And so we need to quickly answer how we can relay the information about the packaged product to the raw materials used in the beginning of the process. So traceability of a product from process step 1 all the way to, say, shipping to a customer is not normally a trivial task because of all the disparate data systems that we have that aren't necessarily connected. So as an example, say we have a defected product identified as defected during a quality control step after a bunch of process steps have already been applied to that product. So a step performed after some processes were done on this product. We need to trace that part back to the process that produced the part in order to paint the picture of what went into the product and kind of create a profile for that product. And so to do this, we need to thread together multiple data sources and systems that are not necessarily easily connected. We also need to make informed assumptions on the sampling frequencies of the data. So to solve the problems that our customers need solved, we need to deal with all these different disparate data systems quickly. We have sensors measuring vibration, temperature, et cetera, taken at various frequencies, and we have quality data like scrap data taken only when scrap events occur. We have maintenance log data taken only when scheduled maintenance is done. We have dimensional data taken on a specific quantity-based sampling plan frequency, and all of these sources have potential importance. So we take the data and stitch it together and merge it and clean it and scrub it to provide and aggregate it as well to provide a holistic view of the product manufacturing cycle, which in turn allows us to explore features that we couldn't explore before. And so these are like the two examples that we're picking out right now that are common challenges that we run into during the exploration of feature engineering step, and a few of the ways in which we aim to quickly solve these challenges.
Okay. Well, as you have described, you have mentioned just two challenges, but you also said that there are some interesting aspects to go through when you go through the whole process. So it's not the only two challenges that you're facing. And, I would say that to me, data science is high risk, high return. That's what I usually talk and explain to our customers. Why it is high risk? Well, because before you actually get into the data and before you explore the data, you cannot guarantee the result. You cannot guarantee that you will solve the business problem that is stated, because it all depends on the data, right? But it is at the same time high return, because if you do, then you can improve just with mathematics, you can improve your scrap, you can improve your throughput, you can save a lot of money not to invest into new assets. You can just improve it with algorithms and with applications. So it's high risk, high return, which means that our goal as a data science services team is to reduce these risks for the customer and, of course, for ourselves. And that is what we have learned over 150 engagements that I've mentioned in the last 4 years that we have done. What you can see on the screen right now is the framework which we are using when we are executing those data science engagements for manufacturers. And we are reducing this risk of doing data science on each step of this process. So first, we always start from preparation when we do executive briefing, when we explain what data science can do and cannot do to the executives of our customers. Technology briefings, when we try to understand what are the current solutions that customers are using and why they are not satisfied with them, how we can contribute to these solutions, and outcome qualification. If at all we will solve this problem, how valuable will it be for the customer? What will be the payback period for that? So that's how we start, and then immediately if we see some roadblocks, then we postpone the engagement. So we are reducing this risk right away. We are helping the customer to understand if it makes sense to continue or not. Then we go into the workout. The first day we talked about the business outcomes and KPIs, how we will measure those business outcomes. The second day we talk about data sources related to these desired business outcomes. And we match those data sources to those business outcomes. So we have a methodology how to go through this 2-day exercise, 2-day workout together with the customer. And again, by the end of this 2-day exercise, we are reducing the risk of investing into data science. So we have invested a little bit, but not too much. And then we go through the process that AJ has described. Usually we are targeting 3 months engagements, but we have as little as 1 week, as small as 1 week offerings, and of course we have a longer engagement if the problem is more complex. But on each step of this iterative process of data science, we have adopted agile project management, which helps us again to control those risks. And if we don't see enough data on a customer side, we go back, we ask for more data. If there is not enough data, then we pause and we wait until data is available, and so on. So we have a special methodology how to run those data science engagements using our agile project management methods. And with that, what I would encourage our audience today is actually to reach out to us. Ajay, if you could go to the next slide. And what we can do, we can go through the first step. We can talk together what are the problems you're facing, and we can do this executive briefings, technology briefings, and other qualification. This is a completely free option for you, but we will help you to understand how data science can help to improve your specific manufacturing processes and solve your manufacturing problems. For 30 minutes, we would like to, to pause here and see if you have any questions. Corey, if you could look at your chat window
Sure.
and see if we can answer some of them.
Absolutely. So we got a bunch. Appreciate that from the audience. So the first one we'll jump into. So Sergey and AJ, how do you assess the value delivered from a data science engagement that you've just described?
Let me try to take it. So how we assess the value delivered from the data science engagement? Well, we try to think about that upfront. As I said, this is first. So what we do, we call it the value map. So we do this value mapping, and through mapping the value for the customers, we are actually doing these calculations. So we specifically calculate together with the customer what will be the benefit from reducing the scrap by 1%. And then we compare that to the investment that is needed to achieve this goal. So this is what we do upfront, and then based on our recent projects, well, the only way how you can compare is actually to see the real results. So you're running this analytic for the next, let's say, 6 months. AJ, you can maybe contribute here, but you're running for the next 6 months, and then you compare to the previous 6 months of work. And then, of course, you need to have a customer's buy-in that, yes, that's a fair comparison. All the other parameters are pretty much the same. And then you can say that, yes, that was the exact benefit from this data science engagement.
Sure, yeah, I think that's a great answer. Along with that, I would say that right up front, the success criteria that we establish is definitely tied to money. It really is the high-level question is how are we saving or increasing, how are we saving money or how are we increasing revenue, or what exactly, how does our metric tie to money? So that's something that is definitely something that we approach right at the beginning. And then by the end, as we increase our scores, our KPI scores or metrics, they have a direct impact on money that we can measure because we've already established the relationship between the metric and the actual outcome of increasing or decreasing cost or revenue.
Got it. Okay. And a follow-up to that is, so what would a typical outcome be from one of these data science engagements? Is it a custom analytic, a new way to maybe frame a business problem and having a KPI that now gives you visibility into that business problem? Would that be potentially, an outcome of one of these engagements?
Yeah, absolutely. I'll start, and then Sergey, maybe you can chime in as well. But definitely, I believe that that's exactly what happens here. And every situation is a little bit different in terms of the outcome that the customer is expecting. So it could be something like what we did and what I talked about with additive manufacturing and developing a real-time or near real-time solution to try to detect some type of defect happening, as well as it could also go all the way to creating a new analytic for someone to just monitor on their own. So there's definitely a wide range of solutions that we offer, but no matter what, we always try to offer some type of insight that will help the business improve.
Well, talking about you asked kind of two questions, if I'm not mistaken. One is what are the deliverables, and the other is what is the outcome. So outcome, AJ has addressed this question. Deliverables, we can obviously clearly see two types of deliverables. One, it can be if it is a root cause analysis, for example, for scrap or for fluctuations in cost, then it can be just a report, because that's enough to go and fix the problem if you prove mathematically that was the root cause. And another option is the live application, which is running on real time. So the application that AJ has showcased today, this 3D metal printing, that runs in real time and saves lots of money, because otherwise they would have to scan each metal part after it's been manufactured. Now you don't need to, because you're controlling quality with machine learning in real time. So that are the two options of deliverables that we can produce.
Fantastic. Well, looks like we're about at time. We really appreciate everybody for joining. Again, if you're interested in having just an introductory conversation around what data science could look like for a potential use case, please reach out to Sergey or AJ. You can also go to ge.com/digital services, and that'll take you to our webpage to learn a little bit more. Otherwise, we look forward to continuing the dialogue with you on another platform. Thanks, everyone, for joining.